So this worksheet is where I gather together questions associated with qualitative inorganic analysis. In other words, seeing what's there, and it's pretty much always seeing what ions are there. The tests can be split up into three groups. Flame tests for certain cations, reactions associated with certain anions, and then solubility, thus making precipitates associated with cations and anions. I want to start off with my solubility rules, putting everything together instead of thinking about them in little bits. So rules 1 and 2 talk about respectively cations and anions that always give you soluble ionic compounds. Rule 3 talks about the halides. Halides generally soluble, and there are the exceptions. The exceptions you need to know for chloride, bromide and iodide. Pretty much the first three: silver plus, lead 2+, and copper 1+. Fluorides you don't tend to need to know for A-level, but we might as well stick them there for completeness. Sulfides, or sulfates, excuse me, very, very important, associated with lead, but also with the heavier alkaline earth metals, so calcium sulfate, strontium sulfate, barium sulfate, all insoluble. Hydroxides you need to know, insoluble, other than the alkali metals, ammonium, and then strontium and barium. A-level tend not to talk about sulfides, but it's a very important one chemically. A-level does talk about carbonates and very occasionally phosphates. Carbonates, phosphates, insoluble, unless the cation is an alkali metal or ammonium, which we've already talked about in Rule 1 anyway. So I'll be referring back to this chart without more expansion as appropriate as we go through. So as far as the order of these questions, pretty much just plucked them out of the A-level exams. There wasn't really any point in separating them out because so many are together. First one, Unit 2 from the old syllabus, but this stuff hasn't changed at all. So Ewan and Gwyneth, 4 unlabeled bottles. They know that these contain these 4 solutions. Complete the 3 empty boxes with the observations expected in each cases. So they already told us that potassium carbonate and magnesium nitrate give a precipitate, barium chloride, potassium carbonate give a white precipitate, and sodium hydroxide and potassium carbonate, no visible change. So now let's see what's happening in these other 3 boxes. First thing to always do is to break the ions, or break apart into the ions. So magnesium Mg2+, nitrate NO3-, Ba2+, Cl- for barium chloride, Na+, OH- for sodium hydroxide, and of course K+, and CO3 2- for carbonate. Because if you've broken them apart into their ions, actually physically write out what the ions are, it should help you analyze things a little bit more easily. Because of course, with very few exceptions, when you mix together 2 ionic compounds, what you're interested in is the cation of one going with the anion of another. So let's look first of all at this box here where we've got Ba2+, Cl-, Na+, and OH-. So cation of one, Ba2+, with anion of the other, OH-, and of course the cation of the other, Na+, with the anion of the first, Na+Cl. What do we know about these? Well, we know that barium hydroxide is one of the soluble hydroxides, and anytime you see sodium, you know it's soluble. So both of these are soluble, so you're not going to see any significant change there. How about this box here, where we've got magnesium would go with hydroxide, and sodium would go with nitrate. Well, now in this case, magnesium hydroxide is not one of the soluble hydroxides, and so it is insoluble. Na, of course, anytime you see that, you know it's going to be soluble. So what we'll see, though, is we'll see that white precipitate of magnesium hydroxide. Finally, this box here, possible products, barium goes with nitrate, or magnesium goes with chloride. Well, all nitrates are soluble, all chlorides are soluble except for the exceptions, and magnesium is not one of those exceptions, so thus no visible change there. Continuing with this, and of course now we filled in the chart in the previous part, name the white precipitate formed when magnesium nitrate is mixed with potassium carbonate. So that's this white precipitate here. So again, we've got magnesium nitrate, potassium and carbonate. Anytime you see potassium or nitrate, you know that it's going to be insoluble, but you take the magnesium and the carbonate, so magnesium carbonate, you make magnesium carbonate there. And all carbonates are insoluble unless the cation is an alkali metal or ammonium. So therefore we have made magnesium carbonate solid by taking the magnesium ions plus the carbonate ions in aqueous solution going to magnesium carbonate solid. Gwyneth uses different tests to identify solutions. Each test allows it to distinguish between some of the solutions. For each test state, the solutions would give visible change observations that would be made. Before we do that, think about what we see with this. Well, litmus, of course, is red in acidic, blue with hydroxide, so therefore a test for hydroxide. Flame tests give you different colors for different cations. And when you add sodium sulfate, adding the sodium means nothing. Sodium's always the spectator ion. But if you've got sulfate there, then there are various ions, various cations that have insoluble sulfates to give precipitates. And as said before, first three you don't really need to know for A-level, but calcium, strontium and barium you definitely need to know have insoluble sulfates. So let's look at our solutions and see how we would test for those. Okay, well, again, split them up into their ions so we can identify things more readily. The only one that has the hydroxide, so therefore would go blue with litmus, is the sodium hydroxide. Flame tests, well, potassium gives a lilac flame, sodium gives an orange flame, barium gives an apple green flame. Now do note, of course, that it's very, very easy for everything to be overwhelmed by this orange, so you need to look through a cobalt blue glass plate or something cobalt bluey, usually a glass plate, which would remove the orange and therefore you could see the lilac. Apple green, a little bit easier to see than the lilac, but even so you really do want to look at these things so that in such a way that you eliminate the orange that's going to be there an awful lot of the time. Magnesium doesn't have a good flame test. Finally, we add sodium sulfate in there. That's going to precipitate with certain cations, not with potassium, not with sodium, but will precipitate, giving you a white precipitate if you've got the barium in there. Okay, so essentially you can use flame tests to determine potassium carbonate, plus of course the various precipitates we talked about. Sodium hydroxide, blue with litmus, and you can see a nice flame. Barium will give you a distinct apple green flame, or the precipitate with sulfate, and you can get to the magnesium nitrate simply by a process of elimination. There are tests out there for magnesium and nitrate, but Gwyneth didn't know those. Ewan and Gwyneth still provided with a white solid they believe is sodium bromide or sodium iodide. Dissolve the solid in water to make a solution. What happens when ionic solids such as sodium bromide dissolves in water? Well, it dissolves to give you the aqueous solution, but then this is not the whole picture because it dissociates, giving you the separate cations and the anions, which is what gives us the chemistry we can do, because the sodium always just floats around as a spectator ion and the bromide has some fun little reactions that it can do. So Gwyneth uses aqueous silver nitrate to identify the solution. Observations expected when silver is added separately to these solutions. Well, silver nitrate is Ag+, and nitrate is a spectator ion. So it's how does the silver behave with the anions. If you've got an anion of bromide, it reacts with the silver to make the silver bromide precipitate, because if you remember, silver halides are all insoluble, and that is a cream precipitate. Iodide also gives a precipitate with silver ions, the precipitate of silver iodide, that is a nice yellow precipitate. I've never personally thought much about the whole cream bit. Yes, if you compare it to, say, the silver chloride, which the GCSEs and A-level describe as white, you can see the difference, but cream all by itself, tough to tell, but the yellow, very, very distinctive. Now, Ewan thinks a further test is needed to distinguish between bromide and iodide. I would argue against that because cream versus yellow, very easy to tell. But the other test you can do is you can add in ammonia. because if you have dilute or concentrated ammonia, it would dissolve the white precipitate from chloride. We don't care about that. The dilute ammonia won't do anything to silver bromide or silver iodide, but concentrated ammonia is enough to dissolve up the cream precipitate from silver bromide, but wouldn't have any effect on the precipitate for silver iodide. And when bromine water added solution to sodium iodide, reaction occurs. Well, what happens is that the bromine atoms want electrons more than the iodide do. So they pinch the extra electrons from the iodide to make bromide, leaving behind with iodine. Bromine's more reactive because it wants to be reduced to go from bromine atoms to bromide anions more than iodine wants to go to iodide.